So one thing you always try to do is link things together. So I was trying to think of what the connection was between these three talks, and I thought, well, Ernest Hemingway, in addition to being a bit of a downer for other writers, also liked his tipple, and what I'm going to say also has something to do with Proxima b. So Mike talked earlier about the detection of an Earth-like planet in the habitable zone, but just being in the habitable zone, despite that cartoon that he showed of what life might look like there, doesn't guarantee that there's any life. And you'll notice that was pretty barren and rocky, what he was showing there in the artist's impression, because of course the artist hasn't been there either. And so the question is, how are we going to detect these planets? And again, in Mike's talk, he talked about, how long it would take Usain Bolt to get there, and even if he'd traded urine through the door in a Russian Olympic village, he still wouldn't have been able to speed up to the point where it would have taken him anything under 100 million years to get there. So we're not going to do this by going there. No matter what the NASA budget is, even if it's huge, we're not going to have enough money to get probes in a reasonable amount of time to planets in other solar systems. So we have to have another way. And even within our own solar system, with a very few exceptions, we haven't done any digging where we actually go somewhere, land, and dig something up and measure it. So we have the first problem, how we find out about things we can't touch. And then what does this tell us about life? So what I study generally are planets that are forming. So here's an image of a solar system in formation, where you're seeing the star that's in the middle, that's buried in that dark lane there, illuminating the disk around the star, and then a jet. This is a real picture, by the way. This is not an artist's conception. The planetary disk is there in the middle. You're seeing these contours of it. And these planetary disks then form planets, and in some cases, planets that are something like the mass of the Earth manage to form in a region where water is between the freezing temperature and the boiling temperature, which is what we generally refer to as the habitable zone. But you have two problems. First of all, you need to be able to figure out how to measure the property of these planets, and then you need to figure out whether that means that there's any prospect that there's real life there. So the way we do this is with devices that are built to break the light up into little pieces, and Mike again showed how we use those to measure the change in the velocity, the wobble of the planet as it goes around the star. But it also gives us information about the property. So this is a gadget we built over the last 5 or 6 years and put out at McDonald Observatory after spending about 20 years making that little green thing in the middle there, which gives this thing its magic. The problem is the planets are typically cool, and they're fairly red, and the stars are hot. And you want to go to wavelengths, at long wavelengths, where the cooler things are relatively brighter compared to the hotter things. And so we move into the infrared. And this is a gadget that's enclosed in a box and cooled down to very low temperatures to measure the spectra of planets. So when you want to do this, you have the advantage that in some cases, the planets will orbit in a way that if the plane of the orbit is just right, and the Kepler satellite was specifically put out to detect planets like this, then the planet would pass in front of the star. And when it does that, even though the planet itself is not very bright, the planet is obscuring part of the star, and the star's light dips temporarily. So the Kepler satellite detected many planets like this. It was designed to look at a particular part of the sky that's pretty far away, and so the stars that it was looking at were all pretty faint. There's a new satellite that's going up next year called TESS, or this year actually, that's going to look at stars that are much closer by and therefore much brighter for these characteristic dips. And if you've ever seen a picture of the Earth from space, you know that there's this kind of aura around the Earth that's due to the Earth's atmosphere and the light from the sun filtering through the Earth's atmosphere. And as it's filtered through, it's absorbed partially by the by the atmosphere of the Earth. And that absorption is not the same at all wavelengths. At some wavelengths, it absorbs more than others. So if you take a spectrum, like with that instrument I showed you, normally we're using it as we do in this bottom spectrum. This is a spectrum of a star that's been extracted from such observations. And that's got a lot of lines in it that come from atoms in the atmosphere of the star, where that atom, in jumping from a lower state to a higher state in the orbits around the nucleus, will absorb energy from the star and take light out of the energy that's coming to us just at that one wavelength. And by looking at which lines are there, you can tell not only what atoms are there, but how many of them are there, what the pressure is in the star, what the temperature is, how strong the magnetic field is, and whether it's wobbling. So you can tell quite a lot of things. But one of the things that's a real nuisance is that this light, when it comes to the telescopes that we look at through, comes to us through the Earth's atmosphere. And the Earth's atmosphere, of course, has a lot of gas in it, as you might be very thankful for. And that gas also absorbs at certain wavelengths. So in the top picture, you're seeing wavelengths at about 2 microns, at about 3 times the wavelength of visible light, 4 times the wavelength of visible light. And all those dips you see are due to carbon dioxide in the Earth's atmosphere. So when you get in your car and go home tonight, that means that next week when I observe this again, those lines will be just a little bit deeper. And so we can recognize that there's carbon dioxide in the Earth's atmosphere this way. If the Earth were a planet passing in front of one of these stars in the distance, and we took a spectrum of the star before the planet went in front of it, we'd see this spectrum at the bottom. And then when the planet passed in front, superposed on it in much tinier form would be this spectrum of the filtered light from the Earth's atmosphere. But you might expect that light to be on the order of 1 million times, even in the case of Proxima Centauri b. You might expect that to be very much fainter. And as a result, you have to have very good large telescope, very sensitive spectrograph, so that you can measure these things. So you get super high signal noise. You have to do it over and over again. And then you have to kind of stack these lines on top of each other. But if you do that enough, you can start to infer what molecules are in the atmosphere of that planet and where they are in the atmosphere by how much broadening there is, whether there are winds. You can learn all sorts of things about the atmospheres of these planets, but it requires really big telescopes, really sensitive spectrographs that look at a lot of lines at once to do it. And when you work through the numbers, you have to take one of those telescopes like the EELT, which used to, I didn't have a name with it, it had outrageous in the title at one point, but overwhelming. I thought it was outrageous, but only the price was outrageous. In any case, you need to take one of these really big telescopes that takes in a lot of light and add together the light from all these different lines and do it from many passages in front of the star in order to get the signal up. And then you might hope to see things. So you need one of these super big telescopes like this in order to do that. Now, the problem is that you have to then say, well, what's going to tell me that there's life there? And the characteristic of life is that it drives the chemistry out of the equilibrium that you would expect just from what the temperature of the planet is and its composition. And what people tell us is that one of the most likely good biomarkers is the presence of oxygen. So molecular oxygen wasn't present in our atmosphere originally. When the plants came along, started breaking up CO2 and breaking up other oxidized molecules in the soil, then you wind up with atomic oxygen in the atmosphere. I've been to some meetings recently where people are arguing whether you could make this in a non-biogenic way. That's something that's still under debate. So the other thing is that you can drive out of equilibrium is the isotope balance. So many atoms have different variants, like carbon has carbon 12, carbon 13, carbon 14. Oxygen has various variants as well. And normally, under normal circumstances, you'd expect the abundance of molecules having these to be in a certain balance, but that balance can be driven away by biogenic processes. And so there are various indicators might give you an idea that there's life. There's a possibility of using something like the spectrum of chlorophyll, but the problem with that is it's a very broad spectrum, and it's very hard to sort out from the spectrum of the star. These sharp lines, like the lines we saw from CO2, are much better in that. So what we hope to do is, by very painstaking work, like this work that Mike talked about Proxima Centauri b, better not mention it again. When he talked about that star, that it took 12, 14 years to get to the point. We expect this to be a long process. Once we get one of these big telescopes online with the right instrument, it's going to take a long time to figure out how to beat down the systematics to get to the point where we can do this. And then all the astrobiologists are going to sit there and argue about whether what we've detected really indicates that there's life there. But we're not going to get there anytime soon, even if we have something more like the satellite that went to Pluto. So if we don't want to wait 80,000 years, and I don't think even the youngest people in this room can afford that, then I think we're going to have to hope that we can do it this way by inference from the spectra. So this is actually my last slide. Mike talked about falling cows, and I just wanted to point out that one of the planets that we're hoping to find is our planet, not Earth, I mean, this one. And so my hope is that maybe certain other signatures that would arise under certain circumstances that would permit us to detect the planet that really should belong to us. So thank you.
Thank you, my favorite Martian. So we have time for a few questions right up front here.
I'd like to reverse engineer your talk for a second, just hypothetically. Okay, now, what kind of signature could we expect? Very, very defined compared to, there's a few bacteria here. No, this is a very
right. So the question is, would a planet that was very rich in life look different from one with a few bacteria here and there? Certainly. I mean, in fact, people argue about Mars today that, people have seen occasional evidence for local bits of methane. This is very under dispute. And whether that's now, bacteria that are under the ground that are essentially bubbling up methane is an argument. But methane's pretty easy to generate in other ways, and it's very abundant in the early solar system. So all it has to do is melt, and you'll have some methane. So that's not a very conclusive thing. If you had a huge amount of life, you would see these broadband signals like chlorophyll and things like that. If it's like ours, of course, and if you have the ability to detect that. Our problem is very fundamental, which is these planets are a tiny fraction of the area of the star is covered when the planet goes in front of it. So the signal is a tiny fraction of the brightness of the star. And you have to somehow extract this little signal. So it's only going to be the very most prominent markers that we can see. And we're never going to get down to sophisticated things like seeing what's the balance of plant and animal life or things like that in the near term.
You, sir? Yeah.
You just made an interesting point about life as we expect it. And, I was very interested a few years ago they found those little worms down in volcanic depths of the ocean.
Right.
Would the same type of
right.
still be
So the question is about this ecology around the deep ocean vents, where you have the tube worms that live on hydrogen sulfide and these other neat things. And the answer is, if there's a closed ecosystem like that, it's not really spitting much stuff out. So it would be very tough to find. Where you might hope to see something like this on Europa, for example, if we send a satellite to Europa and drill a hole in the ice and stick something down, we might be able to sample the water and analyze it chemically and see whether there are signs of non-equilibrium chemistry that you might attribute to life, even if you can't like find zooplanktons or something in there. But these kind of self-contained ecosystems, like you might expect on Mars, there may be if there was life on Mars 3 billion years ago, that then when the planet became colder and drier, was killed off on the surface, it might have retreated deep underground. On the Earth, if you dig 100 meters underground, you're still finding bacteria. But of course, that stuff is not signaling us. It's not sending out material, which is essentially gas, is what we need. They need to exude something before we can find them. And these closed systems will not do that. So no, they're going to hide from us.
The young man up front.
Right. So the question is, how are we going to detect Earth-like planets if it's all filtered through the Earth's atmosphere? This is where the trick of the wobble comes in for you, because every solar system is moving with respect to the Earth and the sun, and the Earth is going around the sun. So there are certain times of year when, if the Earth is going away from the object or towards it, where the lines from that planet as it comes in front of the star will be at a different frequency or a different wavelength. They'll be a little bit to the blue or a little bit to the red, where they would normally be from our perspective. And when they're there, we can catch them. If they're if we're at the exact same velocity, if we're at rest with respect to the planet, we can't see through. So it's an additional factor. In addition to the planet having to be in front of the star, it also has to be at a time when the Earth is either moving towards the object or away from the object to make it work. So it's a very good question, and there's an additional trick and additional complication that comes about when you try to do this.
Yes, sir?
If it were up to you and your option were on the table, would you rather have advances in the detection of the gear on Earth or in orbit, or that idea that we can actually send something over there, get little pixel pictures and send it back? Which one, if they asked you, who would you prefer?
Well, I haven't followed exactly how they're working out, but there are several other problems they got, which is, of course, problem number one is they have to send the signal back. So just this little, 15-ounce thing is somehow got to get a signal across 4 light years back to us. And the other problem is it's going at 0.2 the speed of light and nothing's slowing it down. So it's not going to spend too long anywhere. I mean, you think about how long does light take to travel across the solar system? It isn't too long. So if you think about the baud rate you're going to have with your weak signal from that distance, how many pictures are you going to get? Are you pointed in the right direction? You'll have what? In terms of the habitable zone about Proxima Centauri at 0.2 the speed of light, you're going to cross it in about 30 seconds. And so, how many selfies can you take in 30 seconds? And how long does it take you to send them back? It's a bit of it's a tough problem. So unless the thing gets up to a decent mass where you can really record the information, the way with Pluto, they flew by Pluto pretty fast. It was a number of hours, and it took 6 months to send the data back to Earth just from 200 astronomical units. So you go to 200,000 astronomical units, that's 100,000 times farther. So you're down by about a factor of 10 billion in signal, right?
Oh, great. Well, with that, let's thank my favorite Martian.